Okay, now we're going to talk a little bit about the Schwarzschild radius of a black hole. In a previous video, I showed that the escape velocity from a planet is equal to square root of 2g mass of the planet over the radius of the planet. So if we wanted to find the escape velocity from the Earth, we would use the mass of the Earth over the radius of the Earth. If we wanted to do another planet, we could use the mass of that planet divided by the radius of that planet. So now, how do we apply this to black holes? Well, black hole is an entity which we know from astronomy. It's caused by the implosion of a star. After the star reaches its final stage and it reaches its iron core, the star implodes and explodes, and the core of the star keeps imploding, and we have an event known as a type 2 supernova explosion. And the core of the star forms a singularity. It just keeps collapsing and collapsing and collapsing and becomes infinitely small. So we have some entity here which has mass, and it's a singularity, so it's basically infinite curvature of space-time. So it has a certain mass. Usually the mass of black holes ranges from about 3 to 15 solar masses, the mass of the sun. The most minimum mass of the black hole could be about 3 solar masses. So there's going to be a region around that singularity where gravity is going to be so strong that to escape from that you're going to need a speed faster than the speed of light. So this is known as the edge of that region is known as the event horizon. Okay? And the velocity of escape, if a rocket wants to escape from here, the velocity of escape is greater than the speed of light. Right at the edge of the event horizon, the escape velocity is equal to the speed of light. Well, nothing can go at the speed of light, so you can't even escape from the edge of the event horizon. So the velocity of escape here is equal to the speed of light. So how big do we expect this to be, the radius of the event horizon? Well, we could put here velocity of escape is equal to c square root of 2gm over r. Square both sides. You have 2gm over r. Then we have r is equal to 2gm over c squared. This is known as the Schwarzschild radius. Okay, radius of the Schwarzschild radius, or we can say radius Schwarzschild, RS, 2gm over c squared. Let's see what this is going to come out if we put mass of the sun over here. So this is the values of the g, the mass of the sun, and speed of light. So if a solar mass star could have become a black hole, what would its Schwarzschild radius be? So this will tell us. Well, once you calculate this, you end up getting a 2.95 kilometers. 2.95 kilometers. So roughly about 3 kilometers. So since we said over here that the lightest black hole is 3 solar masses, mass of a black hole is equal to 3 solar masses, well, then it's going to be 3 times this, right? You can see here that the Schwarzschild radius is linearly proportional to the mass of the star, right? So if it's 3 times mass of the sun, it's going to be 3 times that. So the Schwarzschild radius is going to be 3 times 2.95. So that's going to be 8.85 kilometers, roughly 9 kilometers, right? So we could approximate this as 3 kilometers and approximate that as 9 kilometers, okay? If the mass of the black hole is 15 solar masses, okay, then the answer is going to be 15 times whatever this one was, right? 15 times 3. So that's going to be about 45 kilometers. So I kind of think of this kind of black hole as universal trash dumping site. So if we can't find one of these black holes, bring it near Earth, we can take our extra trash and dump it there. As we dump the trash there, mass gets accumulated to the black hole, and as its mass gets accumulated, the black hole grows a little bit. But it grows so very slowly that we could use it for trillions of years. Because imagine we found a black hole that was 3 solar masses, and we kept feeding it mass. But in order for its Schwarzschild radius to go from 9 kilometer to 45 kilometer, okay, we would have to feed it how much mass? Well, the difference between 15 and 3 is 12 solar masses. So in order to grow it from 9 kilometer to 45 kilometer, we would have to feed it a mass equal to 12 times the mass of the sun. Well, that's a lot of mass. So it's not going to grow really that rapidly. So we could just have it there available and take our trash there yearly and dump it in the black hole. So it's kind of an interesting science fiction type of scenario. Now, we also know that there are very huge supermassive black holes in the universe. These are usually centered at the center of massive galaxies. Often these are called active galaxies. So the Milky Way, for example, is housed to have a black hole roughly about 4 million solar masses. Okay? So what would its Schwarzschild radius be? So the Schwarzschild radius is going to be 3 kilometers times 4 times 10 to the 6th. So it's going to be 12 million kilometers, right? In the Schwarzschild radius. Is that pretty big? Well, we know that 1 AU is 150 million kilometers is 1 AU. That's the distance between roughly the distance between the Earth and the Sun. So 12 million divided by 150, so it's going to be 12 divided by 150, 0.08. So 0.08 AUs. So the Schwarzschild radius of the black hole at the center of our Milky Way is 8% of the distance between the Earth and the Sun. 8%. So if you visualize this, okay, so 10% of the Earth's orbit is this much. 8% is about this much. So imagine this big, okay? So if we put that black hole that is at the center of the Milky Way here, okay, it would have a Schwarzschild radius like this. That would all be black. Anything that comes close to that gets sucked in, right? So where would Mercury be? Well, Mercury's orbit is about 0.3 of Earth's orbit, 0.3 AU, so 0.1, 0.2, 0.3. So Mercury would be here. Okay? Would Mercury be safe? It probably might be safe. Okay? Well, of course, it would have to go faster. The mass of the black hole is going to be quicker. It would have to be faster. But if it has the sufficient velocity, it might be able to keep going around for a long enough time. But if it gets closer, too close, if it starts reaching the event horizon, then it will get sucked in. So you can kind of have a visualization of how big of an event horizon this is. What if we imagine another supermassive black hole? At the center of the Virgo galaxy, there's a black hole roughly estimated to be 3 billion solar masses. Virgo galaxy. 3 billion solar masses. Billion kilometers is 1 AU. So 9 billion, a billion is 1,000 million, right? So this is going to be 9,000 divided by 150 AUs. So 9,000 divided by 150, that's 60. 60 AUs. So the Schwarzschild radius of that black hole, if you place it at the center of our solar system, It engulfs our solar system. Of course, it engulfs the Earth. It engulfs Jupiter, Saturn, Neptune. It's sufficient to engulf Pluto. Pluto has a distance of 40 AUs. It could go 50 AU, 60 AU. It's sufficient to engulf all of our solar system. So that's how supermassive of a black hole that is. So now you can kind of see from this the relationship between the size of the event horizon, the mass of the black hole, and how big it can be, and then in relation to our solar system, what its relationship is. Thank you very much.